Kubernetes, container orchestration at scale. Agenda, container orchestration systems. Kubernetes history. Why Kubernetes? Kubernetes architecture, pod lifecycle, getting started, basic workflow, container orchestration. Container orchestration automates the deployment, scaling, networking, and lifecycle management of containerized applications. If a container crashes or a node fails, the system automatically reschedules it elsewhere. Almost all production-grade container deployments run on some kind of orchestrator. Any team running containers at scale relies on orchestration to stay reliable. Manually babysitting containers across many hosts doesn't scale. Single host and cluster systems. A single host setup runs containers directly on one Docker engine with no cross-machine coordination. A cluster-based system like Kubernetes pulls many machine nodes into one logical, schedulable unit. Single host, plain Docker engine, Docker run on a lone VM, no automatic failover. Cluster, Kubernetes, Docker Swarm, Nomad. Problems without orchestration. Single point of failure, one host crash takes every container on it down with it. No automatic rescheduling when a container or node fails. Manual, error prone scaling up or down as traffic changes. Difficult to manage service discovery and load balancing by hand. Rolling out updates safely requires custom scripting. Misses out on declarative infrastructure and GitOps style deployment. Kubernetes container orchestration. Desired state is declared in YAML manifests and kept in a source or Git repository. Container images are pulled from a remote image registry, such as Docker Hub, GCR, or ECR. Kubernetes continuously reconciles the live cluster state to match the declared desired state. Other similar orchestration systems: Docker Swarm, Apache Mesos, Nomad. Kubernetes advantages: automatically heals itself by restarting or rescheduling failed containers. Scales applications up or down automatically based on load. Makes deployments consistent and repeatable across dev, staging, and production. Built-in service discovery and load balancing across pods. Rolling updates and rollbacks with zero downtime. Huge ecosystem of tools for CI/CD, monitoring, and security. Declarative and self-healing. You describe the desired state. Kubernetes control loop continuously works to make it real. Failed pods are automatically restarted or scheduled onto healthy nodes. Config and secrets are managed centrally and injected into workloads. Horizontal scaling can react automatically to CPU or custom metrics. A single node failure has minimal impact. Workloads simply reschedule elsewhere. Pods and services. Pods, the smallest deployable unit, one or more containers that share storage and network. Services, a stable network endpoint that load balances traffic across a set of pods. Deployment manifest. A deployment manifest declares how many replicas of a pod should run and how to update them. Service manifest. Here a service exposes the deployments pods behind a single stable virtual IP and DNS name. History originated from Google's internal borg system, which ran containers at massive scale for over a decade. Released as open source by Google in 2014, the name comes from the Greek word for helmsman or pilot, donated to the newly formed Cloud Native Computing Foundation (CNCF) in 2015. The seven spokes on the Kubernetes logos will reference its original internal codename, Project 7 of 9. Now, the industry standard container orchestration platform, backed by every major cloud provider. Why Kubernetes? Portability runs identically on-prem in any cloud or on bare metal. Self-healing automatically restarts, replaces, and reschedules failing containers. Horizontal scaling add or remove capacity in seconds. Declarative configuration infrastructure as version controlled by YAML. Massive ecosystem HAM, Istio, Prometheus, Argo CD, and more. Backed by every major cloud provider and a huge open source community. The kubeconfig file. The kubeconfig file lives at .kubeconfig and tells kubectl which cluster to talk to within the user's home directory, stores cluster addresses, certificates, and user credentials for one or more clusters. Switch clusters instantly with kubectl config use context. Never commit a kubeconfig file to source control. It often contains credentials. Pod lifecycle. Kubectl apply pending. Node assigned scheduled. Containers up running. And kubectl delete terminated. A pod moves from pending to scheduling onto a node into a running state and finally to termination when it's replaced or removed. Getting started with Kubernetes. This leads us to the three commands that get a workload running on a cluster. kubectl apply, create or update resources declared in the manifest file. kubectl get, list running resources and their current status. kubectl describe, shows detailed information and recent events for a resource. Basic workflow, create a Kubernetes cluster on bare metal with kubedm init, kubedm init. Create a cluster in one of the clouds. Write the manifest files and apply the resources from those manifest files into the cluster with the help of kubeconfig file and set permissions and access control. kubectl apply, get, and scale. Some call apply, get, and scale Kubernetes everyday loop. Declarative. Apply the same file again, and Kubernetes only changes what's different. kubectl get gives an instant snapshot of cluster state. Scaling a deployment takes one command, no manual provisioning. Rollouts can be paused, resumed, or rolled back at any time. Works the same across managed clusters like EKS, GKE, and AKS. Integrates naturally with CI/CD and GitOps pipelines. Any questions? Thank you.